this video for Computer Science 9618 A-Level, we're going to be taking a look at main memory management and interrupts. Let's go ahead and take a look at the learning targets so we know what we got to be doing. Cambridge wants us to show an understanding of virtual memory, paging, and segmentation, and that is what this video is going to focus on. We're going to talk about the kernel of the operating system, how it acts as an interrupt handler, paging, virtual memory, and segmentation, the differences between them, how pages can be replaced, and how disk thrashing can occur. Now, this is going to be a two-part video. The first one is gaining a basic understanding, and the second video, we're going to look at past Cambridge exams to actually implement what we learn or go over in this video. So let's go ahead and get started. Kernel and the interrupts. Well, the kernel is the brain of the operating system. Now, it's the core and the main layer between the operating system and the hardware. Now, the CPU checks for interrupts that are happening, and then what is known as kernel mode is entered. Now, the CPU is checking for interrupt signals because they can come from anywhere when we're on a computer. They can come from devices like printers. Maybe we get a paper jam on the printer. Whatever program we're running is going to be interrupted to let us know, hey, the printer has a paper jam. Maybe there's an exception of a program being thrown. Now, you probably have seen this when you try to divide by zero. You can't divide by zero. An exception or interrupt is done. Traps. Maybe a software is trying to install something and they request a specific resource like a disk drive. Are you sure you want to install this on the C drive? Do you want to make changes to the C drive? That has a very high priority. It's going to interrupt whatever you are doing. Now, the kernel does not know what to do right away. It doesn't magically know how to do all this, so it consults a help guide, something known as an IDT. This stands for the Interrupt Dispatch Table. Now, this table shows the appropriate interrupt routine to be used. So this is how the kernel knows what to do. Now, once it knows what to do, it needs to save the process, the program that is running. So it's going to save the state of the process that was interrupted, and this goes on to the kernel stack. It's very important that we save the process while this interrupt is being handled. Imagine you're typing a term paper. You're on page 19 of 20. You're getting ready to wrap it up. Finally, it's all going to be over. And then you get an interrupt, but the process isn't saved. Now you have to start that entire paper over because it wasn't saved. So that's what we mean by the process being saved. Now, once the interrupt is resolved, the process, the program that is running, is restored, and you can go back to having control of the PC. Now, interrupts are prioritized on a level from 0 to 31, where 0 has the least priority and 31 has the greatest. A process can only be suspended if its interrupt has greater priority than the process itself. When you're on your phone and you're playing a game and there's a phone call, that's going to interrupt your game because phone calls have a higher priority than the game. Now, you may not think so, but it does. So we can wrap up this kernel interrupts in 6 stages. Stage 1, the interrupt is received. All other interrupts immediately become disabled because the interrupt cannot be interrupted. Stage 2, the current process is saved on the kernel stack. We want to be able to resume that program once the interrupt is handled. The interrupt is identified and the priority is checked. Is it time or is it necessary to interrupt the current process that is happening? The system jumps to the interrupt service routine using that help guide if it has a higher priority. The process is restored after the interrupt is handled, and then interrupts are restored, so further interrupts can be dealt with as we move on using the computer. All right, main memory management. Now, just like a hard drive can become fragmented, so can RAM. Now, the memory management of an operating system determines where they should be stored on the RAM. Now, when a program starts, memory is allocated by the operating system. Remember, the operating system deals with memory management. And when it closes, the used memory is freed up. So we open that program, memory is going to be allocated. When we close it down, that memory is freed back up. Now, one method is single contiguous allocation. All of the memory is made available to this single application. Now, this is terrible and extremely inefficient. Now, we're going to talk about different types of memory management, and we're going to start with page memory and paging. Now, paging is when the memory is partitioned, meaning it's split into blocks of a fixed size. The physical memory and the logical memory are divided into the same size memory blocks. And this is how it's different from segmented memory, which we'll talk about in a minute. Now, the physical memory blocks, we call those frames. The logical memory blocks, we call those pages. A program is given more pages than what is required. What does that even mean? Well, a program is given more logical memory than what is required, and we'll take a look at what that means. So when you start a program, say it takes up maybe 2 gigs of RAM, it's actually going to take up more than that because more memory is going to be used than what is required. Now, there is a page table that goes with paged memory. Now, page table. When a program executes, process pages are loaded into frames. Now, these are the physical memory blocks. And this is done by a page table. I have an example to show you this in just a moment. Now, this page table maps logical addresses to physical addresses or pages to frames. Each page table has a page number, a flag status, page frame address, and when it entered the memory, the time that it entered the RAM. Because if we ever need to remove it later on to swap it with the hard drive, which we'll talk about in a little bit, we need to know which one has been on there the longest so we can get it off first. So let's look at an example about this page table, these pages, these frames, these page numbers. What does all that mean? So here we have the logical memory. We have page 1, page 2, page 3, page 4. What are these? What are these pages? Well, they reference the page table. Page 1 is pointing to the page table. So right here is page 1. This page table says, okay, you want to access the physical memory. That's going to be on index 2 of the RAM. Now, are they called indexes? Absolutely not. We're just using that as an example for the frame numbers that we have here. So instead of index, I'll use the actual word frame number. Page 2. Page 2 is right here. So we look on that page table. It's pointing to frame number 6. That's where page 2 is stored. If I need to load up page 3, the logical memory says, let me consult my page table. It consults the page table. It says, the frame number you're looking for page 3 is on frame 8. Page 4 says, you need to access page 4. Let me find where that is. It consults the page table and says, you're looking for 4. And then we can find that memory. That is how paging actually works. Now, segmented memory works a bit differently. A segment has a name and it has a size. And I have an illustration for this as well. Logical address space is broken into different size blocks, and this is why we call it a segment. They are not equal size blocks. The segments from logical memory, they're loaded into physical memory, and the address is defined as the segment number and the offset value, which is determined by the programmer. Now, I want to be clear, today, most of this offset is handled by the operating system, but it is possible for a programmer to choose the offset. Now, this allows blocks of various sizes, so we call it dynamic. The blocks shrink and they expand as necessary, unlike paging, where the memory is a fixed size. So in paging, we have a fixed size memory. In segmented memory, we don't have a fixed size. It'll expand as it needs to. It will also shrink as it needs to. So let's take a look at an example. So here we have segments, and these segments are segment memory. Notice they're all different sizes, unlike in page memory where they're of equal sizes. So we have a segment number, segment 0. The base address is 500 and has a limit of 600. That's because right now segment 0, whatever memory that may be, is taking up address 500 to address 1100. Now, there is still room for segment 0 to grow. As we start taking things off, it will start shrinking and actually decrease in size. So you see all these different segment numbers, these are the logical address spaces. So segment 0, we look at 0, it says, hey, it's at 500 is where it starts. It has a limit of 600. Segment 1, we look at segment 1, it starts at 2500, has a limit of 800. So we swing over here to 2500, we see it goes all the way to 3300. That's where we're going to find segmented memory number 1. Number 2 is a lot smaller. So I look at the segment number 2, says the base address starts at 1500. So I go to 1500. It has a limit of 400, which goes to 1900. So here you will see all of these have a offset, and they're all of different sizes, unlike paged memory. Now, let's talk about the differences between them. Segmented memory must be contiguous right next to one another, while paged memory does not. Paging cannot be seen by a programmer, while segmented memory can. Paging has blocks that are fixed, and all of them may not be used. Remember, it's going to reserve more memory than it needs, and this leads to internal fragmentation. Segmented memory has variable size blocks, which leads to less internal fragmentation, but a higher chance of external fragmentation. So there are benefits and drawbacks to each. Now, what if the RAM becomes full? If RAM becomes full, data used in the programs can become corrupted. Now, you can use the hard drive as memory, and we call this virtual memory. RAM is the physical memory. The RAM plus the swap space on the hard drive is your virtual memory. Now, the swap space is the size on the hard disk drive or solid state drive that can load into memory from the hard drive. So we can actually load memory from the hard drive onto the RAM. Now, the oldest used data is the first to get replaced. An existing page number gets overwritten when it's not being used. Now, if you're in my class, you're going to need to go ahead and add that to the outline I provided. All right, so what are the benefits? Why would we use virtual memory? Well, programs that require larger memory than what is available in our computer, in our physical memory, they can still run. There's no need to waste memory with data not being used. The external and internal fragmentation, they become minimized. You don't need to go out and buy more expensive RAM to upgrade your system. So why not just use virtual memory to begin with in the first place? Why is everybody going out and buying these, sticks of RAM that can cost a couple $100 depending on how much you buy, when we can just use virtual memory and swap it out with our hard drive? Well, there are drawbacks. The more data or pages that are loaded, causes a high rate of swapping, which we're going to see in just a minute. Now, this causes what is known as disk thrashing. If more time is spent loading and moving pages, performance slows way down because we're constantly have to load and reload from the hard drive because the RAM's full. We got to take something from the RAM, put it on the hard drive, find what we need from the hard drive, put it back on to the RAM. Now the RAM's full again. It's time to use another piece of RAM. So now we got to find the piece of RAM that we don't need, put it on the hard drive, search the hard drive for what we need, and put that back onto the RAM. That is disk thrashing, back and forth, back and forth, back and forth. Because there is so much read-write head movement, this can cause the hard drive to fail prematurely, and we don't want that to happen. So here's an illustration. So we have our physical memory and we have our hard disk. This virtual memory per process, this is the swap space. We're swapping things in and out. So let's say we need this piece of physical memory at the top. We have to pull it. Well, the first thing we have to do is find the section of physical memory that's not being used. What we have to do is we got to put it and swap it out with a place on the hard disk. After we do that, then we have to find what we need and we have to put it on to the RAM. Now the RAM's full again. Well, guess what? Another process needs to be used. So now we got to find another piece on the RAM that we can take off, put onto the hard drive, and then find what we need on the hard drive, put it back onto the RAM. Because there are things cycling back and forth over and over and over again, this brings a drag on the performance, slowing way down, and you'll usually get a notification that your virtual memory is running low, and when you see that, your computer is going to take a long time to respond. Now in the next video we're going to take a look at past Cambridge questions and put all of this information we learned today to use. Hope you guys found this video helpful. If you did, make sure to give it a thumbs up and subscribe to help the channel grow. We'll see you guys in the next computer science video.